Let's refine our understanding of atomic theory by studying atoms and isotopes. Here's some example of our atoms on our periodic table, elements with 1 and 2 protons. The hydrogen atom has 1 proton. Hydrogen also has 1 electron. There's no problem with the nucleus holding together because there's nothing to drive them apart. And by the way, hydrogen gas comes in packages of 2. We say it's diatomic. H2 is its formula. Helium has 2 protons. You can see there a helium blimp from Lockheed Martin. That's a mock-up. Helium has 2 protons, and it also has 2 electrons. Its chemical properties are different from the hydrogen atom. Helium has no known chemical reactions. That's why it's used safely in balloons and blimps. But with 2 protons, if you think of the nucleus, the charges inside the nucleus repel each other. We'll talk about how this is handled in a minute. Here are the remaining elements on the second period of the periodic table, the second row. Lithium, which has 3 protons and electrons, beryllium, which has 4, boron, which has 5, carbon, which has 6, and so forth up to fluorine with 9 and neon with 10. The properties of these elements are determined by the number of their electrons. Now, the rest of the story asks the question, where is the rest of the atomic mass? We know that helium has 2 protons, which each have a weight of a mass of 1 gram per mole, but it has an atomic mass of 4 grams per mole. So where's the rest of the mass? Well, we have to think the 2 protons will repel each other. So electrostatic force will drive the protons apart, and the nucleus is so small it would drive the protons apart with amazing force. Neutrons are in the nucleus, and their function is to keep the positive electricity together, to keep the nucleus from blowing apart. It's a lot more complicated than that, but that's the only thing we need to remember for now. You can, of course, read up to see how it is that the presence of the neutrons establishes a low energy state in the nucleus and keeps it from blowing up. Here are the common number of neutrons in each of the elements. Typically hydrogen has none, although we'll see in a little while, there are isotopes of pretty much every element. Helium typically has 2, lithium 4, beryllium 5, boron 6, carbon 6, nitrogen 7, oxygen 8, fluorine 10, and neon 10. As the atomic number goes up, what then appears to be happening in general to the number of neutrons? Well, they're going up. And when we add up the atomic number, the number of protons, to the number of neutrons, we get the mass number of that particular variety of that element. Each, however, has the same number of electrons as every other element of that kind. Now, the number of protons plus the number of neutrons is the mass number. The mass number minus the atomic number then is the number of neutrons. Not all nuclei are the same, however. They differ by the number of neutrons. So we have several different kinds of carbon, for instance. If we have the same element but different mass, we have isotopes of that element. Isotopes of a given element all have the same chemistry, but the mass is different because of the number of neutrons. Let's talk then about carbon and use the hyphen notation. Carbon has 3 naturally occurring isotopes. Carbon 12, again there's a dash between the C and the 12. carbon-13, and carbon-14. You can use this notation for any isotope of any element. For instance, uranium comes in several varieties, the most common being U-235 and U-238. Now, from the information available on your periodic table, calculate the number of electrons in a neutral atom of the phosphorus element. You first find the phosphorus, it's element number 15. The atomic number then is 15. The atomic number is the number of protons. The atomic number is then also the number of electrons in the neutral atom of phosphorus. And so the answer, of course, is 15. Neutral calcium-42 has how many neutrons and how many electrons? Well, find calcium, it's element number 20. The atomic number then is 20, and the number of protons is the atomic number. The atomic number is also the number of electrons in the neutral atom, and so there are 20 electrons. The number of neutrons is the mass number less the atomic number, or 42, as you can see up here from the isotope number 42, and you take away 20, which is the atomic number, the number of protons, and so you get 22 neutrons in calcium-42. Now, if you've done the exercise called duck luck, let's remind ourselves of what it teaches. There were 2 ducks out of the 10 that were brown. Their abundance then is 0.2 or 20%. 8 of the ducks of the 10 ducks total were white. That abundance was then 0.8 or 80%. The brown mass duck, 1.5 kilograms each. The white mass duck, 2.0 kilograms each. The average duck then is the abundance of brown ducks times the mass, or 0.20 times 1.5 kilograms, added to the abundance of white ducks, 0.8, times the mass of each, 2. 0.8 times 2 kilograms. When we add these two up, we get 0.3 kilograms plus 1.6 kilograms, or 1.9 kilograms. The brown ducks contribute 20% of the weighted mass, and the white ducks contribute 80% of the weighted mass. And so the weighted average of ducks, the average duck, is 1.90 kilograms. The average is always equal to the abundance of the first type times its mass, plus the abundance of the second class times its mass. Notice that neither of these ducks, neither the brown nor the white, is the average duck. The average duck simply doesn't exist here. It's a weighted average of 2 ducks with different masses and different abundances. Again, whenever we need a weighted average, we take the abundance of the first times its mass, and we add the abundance of the second times its mass, plus the abundance of the third times its mass, and so forth. And all of those added together will give you the weighted average. Now, isotopes do not all have the same abundance. Suppose we had 2 kinds of carbon, carbon-12 and 13. If their abundance were the same, then the measured atomic mass of carbon would have to be 12.5. If the abundance of carbon-12 was 75% and of carbon-13 was 25%, then we would calculate the atomic mass of carbon in nature just like we did the ducks. The mass is equal to 12 times its abundance, 0.75, plus 13 times its abundance, 0.25, or 12.25, if that were the abundances. So the general rule for calculating atomic mass of isotopes, of the average isotope in nature, is the total mass the weighted average mass, is the mass of the first isotope times its abundance in a decimal form, plus the mass of the second isotope times its abundance, plus the mass of the third isotope times its abundance, and so forth. Now, there are two isotopes of chlorine, chlorine-35, which is 76% abundance, and chlorine-37, which is 24% abundant. So let's solve for the weighted average mass that we should put on the periodic table. We know the abundance of each isotope and the mass of each isotope. So the abundance of chlorine-37 is 0.24 or 24%. We multiply the abundance of the 35 isotope by its mass, 35, and the abundance of the 37 isotope by its mass, 37. So 35 AMU times 0.76 plus 37 AMU times 0.24. When we do those two calculations and add them, we get 35.5 AMU. This is a sensible answer, and it's close to what we see on the periodic table. It's sensible because we have more of the chlorine-35 than of the 37, so it should be closer to the 35 than the 37, and it is 35.5. Let's look at element Q, kind of an unknown, has two isotopes, Q300 and 310. If the abundance of Q300 is 66%, what would be the mass of Q on the periodic table? That is the weighted average mass. Now, why don't you do that for yourself and then check your answer when you come back to the video. Coming back, we know that Q300 is 66%, so if there's only two isotopes, Q310 has to be 34%, 0.34. The mass, again, is equal to the abundance of the first times the mass of the first, and this you're going to add then the abundance of the second times the atomic mass of the second isotope. We plug in the numbers, 0.66 times 300 and 0.34 times 310, and we get 198 AMUs from this, 105.4 AMUs from that. The average, weighted average, is 303.4 AMU. This is okay because we have more of the 300 isotope than of the 310, so it should be closer to the 300 isotope than the 310.